Let's look at the development of the continuity equation that will help us solve a number of problems that involve fluid flow. Recall from physics the principle of conservation of mass, that for a system the amount of mass remains constant with time. We're going to use this principle in developing this equation. Let's sketch this pipe that has a varying cross-section. So the diameter on this side is smaller, whereas the diameter on this right-hand side is larger. We are going to develop this continuity equation for this type of a pipe. Although we can derive this equation for a pipe with constant diameter, we want to use a pipe with variable cross-section to show that our development will also be suitable for such type of variable cross-sections. And let's say that the cross-sectional area on the left-hand side is A1, whereas the cross-sectional area on the right-hand side is A2. Let's assume, first of all, that we have steady flow and also that there is no leakage from the pipe surface. Now the fluid in the space x dash, and see that after a small time interval delta t, that amount of fluid moves to a new space of y dash. Distance between x and y is delta x1. Because the right hand side, the cross-sectional area, is much larger, the distance between location x dash y dash is delta x2, which is smaller. The delta x2 is smaller than delta x1. So what we essentially see here is that fluid initially was in x dash, and it moves after a certain time period to a new location y dash. To meet the requirements of conservation of mass, the fluid that is contained between x and x dash must equal the amount of fluid that's contained in y dash. We also note that the fluid in space yx dash is the same for both initial and final conditions. So that suggests that the fluid in xy space must equal the fluid in x dash y dash space. Let's see how much fluid is there in space xy. Note that the cross-sectional area here is A1, and the density of fluid, let's say, is rho 1, and this length we noted earlier was delta x1. So the amount of fluid that's present here is rho 1 A1 times delta x1, and the amount of fluid that is now in space x dash y dash is density rho 2 times the cross-sectional area A2, which is different than A1, times delta x2. Now this change occurred over a period of delta t, the small time step. So we can divide both left-hand side and right-hand side by delta t. So we have rho 1 A1 delta x1 over delta t equals rho 2 A2 delta x2 over delta t. Now note that delta x over delta t is the velocity, the distance over time. So we have rho 1 A1 u1. We will write a u1 with a little bar on its top to say that this is an average velocity, equals rho 2 A2 u2. This is our equation of continuity. Note that we can also express rho 1 A1 u1 as mass flow rate, or with small letter m with a dot on it to express that it is a rate term. And if you want to look at the units, note that rho is kilogram per cubic meters, A is meter square, U is meter per second, and that will give us the units of kilogram per second for the mass flow rate. So we have the equation of continuity also expressed as m dot 1 equals m dot 2, which basically says that the mass flow rate in this system remains constant under steady state conditions. Now, we should also note that if the density of the fluid remains constant as the fluid moved from left to right hand side, and of course it will, there is nothing happening here that's changing its density, so we can actually cancel out the density terms. So rho 1 and rho 2 will cancel out since they are the same, and we are left with A1 U1 equals A2 U2. So this A1 U1 actually is the volumetric flow rate, and we will express that as a capital V or uppercase V with a dot. If you look at the units, note that area is meter square, U is meter per second, so the units for volumetric flow rate are cubic meter per second. So again, in case of our equation of continuity, we have the volumetric rate remaining constant under steady state conditions.